Underneath the metallic skin of a pig transport trailer, an invisible equation is constantly in motion. It's not just about moving animals from farm to plant. It's about how dozens of tons of live mass breathe, sweat, and react inside a mobile steel structure that rarely stops, even under extreme conditions. At first glance, these trailers resemble ordinary cargo units. But when seen through the lens of biomechanical efficiency and structural balance, they begin to look a lot more like something out of a mining operation. Machines built to endure stress without breaking the system that keeps them breathing. In underground mining, ore shuttles navigate narrow shafts while balancing two conflicting forces: mechanical load and ventilation flow. Too much weight, and the tunnel collapses. Too little airflow, and no one survives. In livestock logistics, the same principle applies. Each pig adds biological weight, not just in kilos, but in metabolic heat, carbon dioxide, and moisture. Inside the trailer, air must circulate with millimetric precision to avoid pockets of suffocating humidity. And just like a shuttle carrying ore, the transport unit must absorb vibrations, distribute weight evenly, and preserve the internal environment over long distances and uneven roads. The challenge intensifies with biology. Pigs are highly reactive to temperature and sound. A poorly ventilated trailer can trigger a cascade of stress responses within minutes. Glycogen reserves deplete. Body temperature rises. The meat darkens. The yield drops. In extreme cases, animals collapse before arriving, transforming logistical failure into economic loss. Unlike mineral cargo, these are living organisms under pressure. Their stress is chemical. Their movements are unpredictable. Their stability depends on what engineers call passive resilience, designing surfaces, panels, and shock absorbers that quietly do the work of preserving life under constant motion. And that's where the analogy with mining goes deeper. Ore carts are engineered to withstand impacts while maintaining laminar airflow, an invisible current that keeps dust levels low and systems safe. In pig trailers, air must move not just efficiently, but strategically, from head to tail, across multiple decks, without triggering panic or heat accumulation. But unlike mining, where machinery and tunnels are standardized across operations, pig transport often lacks harmonized protocols. Each hauler may vary in its insulation, vibration profile, and thermal response. The result? Even a small oversight in trailer design or loading sequence can lead to bruising, mortality in transit, and critical shifts in meat pH. What we're looking at then is not just transportation. It's a mobile biomechanical laboratory, one that must integrate body mass distribution, noise control, air exchange, and shock absorption into a single unit. And yet, for all its complexity, the system operates largely behind the scenes. Few people ever witness what happens inside these trailers. Viewers still understand that the journey of a pig is not just a rural event. It's an invisible choreography of weight, breath, and engineering. An underground system, rolling above ground, feeding nations without drawing attention. But that's only part of the journey, because even the best-designed trailer is vulnerable to one of the most underestimated forces in animal logistics: heat. And when thermal density rises, failure begins. Not with a breakdown, but with a silence that builds inside the trailer, molecule by molecule. On paper, most pig transport trailers appear optimized for ventilation. Designers calculate airflow based on the total volume of the cargo unit, install fans or vents, and expect physics to do the rest. But this logic collapses under the weight of biology. A pig is not passive cargo. It breathes, radiates heat, and releases moisture. And when you multiply that by 200, 300, sometimes 400 animals per trailer, the air inside becomes something else entirely: thick, saturated, and dangerously unstable within the first 30 minutes of a static queue. The problem is metabolic, not mechanical. Each pig emits not only heat, but sweat vapor and CO2, creating what engineers call a dynamic thermal load. Unlike the cold steel of the trailer or the fixed ventilation ducts above, pigs respond in real time to discomfort. Their respiration rate increases. Their sweat glands activate. And with every additional degree of body heat, the internal climate tips further into imbalance. The system wasn't designed for this kind of feedback loop, and so the risk rises, quietly, invisibly, and fast. That's why new technologies are no longer focused just on fan capacity or insulation thickness, but on microclimate intelligence. One solution gaining ground is the use of modular evaporative pods, small, integrated climate control units mounted along the roof and sides of the trailer. These pods don't just blow air, they interpret it. Sensors track internal vapor pressure, essentially how much the pigs are sweating, and adjust ventilation flow in real time. It's a dynamic response system built around biological signals, not engineering assumptions. Instead of reacting to external temperature, it listens to the herd, and the numbers justify the investment. According to studies compiled by the FAO, a single-degree increase in internal body temperature can shift the final pH of the meat by nearly half a point. That doesn't just affect flavor, it changes texture, color, and economic value. In over 60% of transported herds, elevated body heat correlates with muscle acidosis, reducing the meat's commercial grade. It's a thermal chain reaction where time and temperature are currencies, and both are lost fast when ventilation is miscalculated. Some logistics hubs are already adapting. In Goiás, central Brazil, a transport cooperative introduced climate-responsive trailers fitted with digital swine thermometers and automated vent zones. The system monitors each section of the trailer, activating evaporative cooling only where needed. In the first 6 months, the operation saw a 28% drop in meat loss per ton. But perhaps more important than the numbers was what changed inside the trailer. Movement slowed, vocalizations dropped, and pigs began to lie down, signs of a stable microclimate, not just a ventilated space. This reveals a deeper truth. Transport climate for pigs isn't about blasting cold air. It's about achieving evaporative equilibrium, the point at which moisture, temperature, and animal psychology converge into a state of calm. Because congestion is not just a spatial issue, it's psychological. Pigs sense humidity the way we sense crowding. And when the air stops moving, so does their stability. Inside that trailer, every breath counts. And the difference between a smooth journey and a stressful one isn't just engineering, it's empathy built into machinery, guided by science and fine-tuned to biology. But even with temperature under control, another force continues to shape behavior in transit, one that has no form, but a powerful presence: sound. There's a frequency you don't hear, but pigs do. It's a low, persistent hum that rolls beneath the metallic chassis of many livestock transport trucks. Especially in rear-engine models, the vibration is constant, spreading through the floor, bouncing against the sidewalls, and seeping into every compartment. To a human, it's background noise, but to a pig, it's something else entirely, a sonic disturbance that can activate stress pathways within minutes of departure. Swine hearing operates in a different range from ours. Their sensitivity peaks between 250 Hz and 2 kHz, precisely where many diesel engines resonate under load. When the engine is mounted at the rear, closer to the animal cargo, this sound overlaps directly with their auditory comfort zone. The result? Agitation, increased movement, and frequent loss of footing. Pigs begin to pace, push against the gates, and urinate more frequently, a biological signal of anxiety. This spike in ammonia, coupled with bruising and muscle tension, leads to lower quality carcasses at arrival, regardless of travel distance. To address this, some manufacturers have reimagined the truck from the frame up. Powertrain components are relocated to the front of the vehicle, isolating the acoustic source away from the live cargo. Acoustic deflection baffles, angled panels of dense composite material, line the trailer walls, redirecting sound waves upward instead of inward. Beneath the pig's feet, rubber-mounted suspension floors reduce vibrational resonance, acting as a shock-absorbent membrane between the chassis and the animals. It's not just insulation, it's orchestration. The impact is measurable. In comparative trials, herds transported in front-engine trucks showed 41% fewer falls and surface injuries than those moved in rear-engine configurations. The data held across identical routes, weather conditions, and load weights. But beyond numbers, the behavioral difference was striking. Where one group arrived restless and alert, the other lay calmly, conserving energy, an internal indicator of low cortisol and muscular balance. In the southern state of Paraná, a swine-producing cooperative conducted a full fleet transition after reviewing these outcomes. They didn't change the route, the timing, or the trailer structure. What they changed was the acoustic profile. Engineers analyzed how exhaust harmonics traveled through vent openings and rerouted them using angled ducts and external silencers. The new configurations didn't just reduce noise. It reshaped the sound environment to match the natural tolerance of the species being transported. This reveals a principle often ignored in livestock logistics. Acoustics matter, not for comfort in the human sense, but for neurochemical stability. The trailer, in this sense, must function more like a precision aviary than a freight container. In bird transport, species-specific hearing thresholds dictate design. With pigs, the same should apply. What matters is not how it sounds to us, but how it feels to them. When mechanical rhythm aligns with biological tolerance, movement becomes safe, not because the engine is quieter, but because its pulse respects the animal's world. And in the high-volume corridors of swine logistics, that respect translates directly into yield, health, and efficiency. But there's a deeper shift underway, because the future of pig transport may not depend solely on trailers, engines, or air vents, but on something smaller, smarter, and far more individualized. A system where each animal becomes a data point, and the logistics chain becomes a living network. Across continents and rural road networks, over 10 million pigs are moved every year through an immense logistical architecture designed to serve a singular objective: preserve biological quality while in motion. Yet this objective can no longer be met by trailers alone. The era of inert transport boxes, disconnected from the animals they carry, is fading. What replaces it is something much more complex and intelligent: a distributed, responsive infrastructure where biology meets data and where logistics becomes a living system. In agricultural engineering, systems fail not because a part breaks, but because an equilibrium is lost. The rotary baler is a classic example. It works only if internal compression and external counterpressure are precisely balanced. Too little resistance at the gate and the core collapses. Too much and the machine jams. The logic is mechanical, but the consequence is biological. In pig transport, the same rule applies. The flow of air, the level of vibration, the gradient of humidity, these are not external conditions. They are structural forces that interact continuously with the animal's physiology. If one variable shifts, the others must respond, or the cost is paid in glycogen loss, meat acidification, and, ultimately, revenue. This is where innovation is now heading, no longer at the level of hardware alone, but at the integration layer, where machines interpret life. In China, a logistics company redefined animal transport using RFID-enabled crates. Each pig carries a sensor that measures body temperature in real time, transmitting data to an onboard algorithm that predicts stress onset. Based on historical patterns and environmental feedback, the system adjusts the trailer's internal environment by segment. It initiates targeted spray cycles, modifies route pacing, and even recommends rest windows. This is not automation, it is biological forecasting, embedded in logistics. And the numbers confirm the shift. With individual biometric tracking, the company reduced in-transit deaths by 63%. But what is more telling is what happened afterward. Pigs arriving from these smart haulers consumed feed more efficiently and adapted faster to post-transport environments. Their immune systems showed less suppression. Their metabolic profiles stabilized sooner. In essence, the transport system didn't just preserve life, it improved performance. These are not minor upgrades. They are structural changes in how agriculture thinks. Each animal becomes a moving data point, each route a dynamic experiment in thermoregulation, acoustics, and behavioral control. Trailers are no longer just carriers. They are interfaces between metabolism and mechanics, between profit and preservation. And in this new model, logistics becomes something closer to precision ecology, a moving ecosystem powered by algorithms, informed by biology, and built to deliver not just animals, but outcomes. In the background of the global food chain, this revolution is quiet. It moves in sensors, in algorithms, in re-engineered engines and redesigned airflows. But its effect is immense, because when the act of transporting pigs becomes this precise, this synchronized, it reveals something profound, that the future of feeding the world does not rest solely in fields or factories, but in the intelligence of everything that moves between them.